We continue today our exploration of the application layer. This is where we stopped last week. We saw how the DNS resolver in a computer has to go to a local DNS resolver that will eventually go to the home DNS server of the domain of interest. The DNS servers of the domain of interest essentially contains a big file which has rows. In every row there are records. A record is typically the mapping of a name to an IP address. It's called an A record, or a quadruple A record for an IPv6 address. So you can query the DNS with NSLOOKUP or DIG as we did in the lab, and you will see, for example, the result of such an extract from the database or for the big file that the DNS server has, which contains also a large number of other types of records. CNAME is the one that we will often see. CNAME is a canonical name. It's a synonym. Typically, servers like generic servers here are mapped to the name of a machine. And if you change the machine, you probably, if you're in a well-managed company like large fractions of Epfl, then you change the name of the machine, and this machine itself has an IP address. The DNS is used also for application-specific records. For example, IP telephony uses the DNS to find what is the IP address that corresponds to someone's number. The mail system uses the DNS to find where is the IP address of the email server that serves a certain email address, and zillions of other things here. We have seen also that an important part of the DNS is that the records are cached. They are cached by all the servers that are not the authoritative servers, the servers that own the domain. And it's the server that controls the domain that in principle controls the cache. I say in principle because, of course, nobody can prevent you to, if you own a cache, you can, of course, change those time to live values. But in principle, this should not be done. For example, here the IBM company sets a time to live of 2 hours, which means that when someone else at Epfl wants to resolve this address, it will be done locally because it's in the cache, but the answer that you receive has a smaller time to live. So if this would be cached again, which is typically done, your device will cache it, then it will expire after some time. I skipped the reverse DNS lookup. The DNS names are given by a root authority, which used to be ICANN, is now PTI. That's the name of a, now we're entering the political era. ICANN was an American company. PTI is now an organization that is set up by more political organizations, I believe the United Nations. So this entity delivers the top level names. At the origin, the top level names were very few. There were the country names. 2 letters are always a country name, like .ch. And there were the 3 letters that were very few, like .com, .edu, etc., which were essentially America-centric names. Now, as we've already discussed, PTI has opened this, so anything can be a top-level name. Info is another example here. We see that we have here the .info. So that means somebody bought this name by paying a fee to PTI, and then it's your business to get money, hopefully more than what you pay for this domain, from those who want to have a name inside info. The 2-letter names are correspond to countries, so every country has to designate a registry. The registry is the legal authority that gives you the name, and then if you have a name, you still need to put in a DNS server, and then this is done by DNS server companies. And to concretely have a name, you also have to buy it from a register. So a register is a commercial organization that sends you a bill every year or every 10 years if you buy it for 10 years. That is separate from the registry. That's simply decides who is allowed to do what. So they used to be the same. Switch was both a register and registry, but in Switzerland, for example, they have been separated. So this is the state of the art today. You have top-level domain names, and then every top-level domain name, including .ch, for example, must organize itself how it resells the different names. And other than that, it's completely liberal. The price of a name is completely decided by the registers here. So Swiss names are a bit more expensive than .com names, for example, but .org names are probably a bit more expensive, etc. There is an attempt to do something radically different. As you see, DNS is a hierarchical system where there's a root and a level of trust that we give to PTI and to Switch, for example, for Switzerland. There is an attempt to do it completely decentralized, that is limited to the .bit domain. So if you want a domain name that ends with .bit, you can use Namecoin, and then there is no authority. It uses blockchain technology to check the names. Probably this will expand in the future, so we will see later whether that replaces the centralized DNS or not. The future will tell. TTL and DNS in DNS records is a very important tool. In fact, we will see that the DNS plays an important role in managing the internet today. Though at the beginning, the DNS was just a commodity. It was because we believed that connecting to something called lca.epfl.ch is simpler than connecting to 128, 178, 156.1. At the beginning of the internet, when I was using email or things like this, we did things like this. So we went to a server. It was not web servers. It was a Gopher or other more ridiculously complicated and low-function servers. You would go there by their IP addresses. So DNS was really meant to be a human-readable form of IP addresses. But it turns out that it has many benefits that go well beyond this. Here is one of them. Assume you have a company like Google or whatever that serves the entire world. So when you click google.com or google.ch, for example, you don't go to one IP address called Google. Instead, what Google does is it puts into the DNS, it uses what is called a load balancing DNS server. So a load balancing DNS server is a DNS server that simply does not do what I presented before. What I presented before is a static list of IP addresses and names, and it changes only when a new machine is introduced or an old machine is deleted. A load balancing DNS server is dynamic, and it has multiple addresses for a given name. Here is, for example, for Softcom, 3 addresses, but as you can imagine, Google can have a much larger number of canonical names or directly IP addresses that corresponds to the same name here. With a very short TTL, here it's 5 minutes. And then, depending on what network management application sees, you may change the order in which you present this in the DNS database, because when your DNS resolver goes to the DNS, it will typically obtain the first answer, or if you obtain multiple answers, it will try the first one, and it will use the second one, only if the first one doesn't. So when you go to this name here, softcom.com, you will get this address, and this is valid for 5 minutes. If 10 minutes later you do it again, you will perhaps get the same, or perhaps another one, depending on the decisions done by this company and the load balancing system for this company. This TTL is very short, in order to allow this to be dynamic. Of course, if we put a TTL of 2 days, there would not be no load balancing possible. This is why Facebook, when the Facebook DNS servers crashed, the whole world did not have access to Facebook names, including Facebook, by the way, because they use those very short TTLs. That's the motivation for that. Of course, this is a very important infrastructure. If you break this, like we've seen in the famous Facebook outage of a few weeks ago, you lose everything for your company here. So we guess Facebook next time will be a bit wiser and will implement that in a more robust way. Security is, of course, vital to DNS. If anyone can forge DNS query, reply, then we can do attacks that are very powerful because they can be remote. For example, instead of going to the Epfl Moodle site, you could go to another site that pretends to be Epfl simply by giving the wrong A or quadruple A record here. However, it turns out that DNS alone, as the protocol I've presented, is unsecure. Again, that's very strange, but this is how the internet was designed in the 70s. People did not think of security as a problem, which is funny because it was funded by the US Military of Defense. So anyone can send incorrect answers to DNS queries. So a very simple attack is you connect a PC to hotspots, a place where people connect in a railway station, for example, and then you try to get through MAC spoofing, you try to get DNS queries, and then you reply to them whenever, or you put a server that responds to this address, for example, here. Of course, this is recognized as a problem, and as much as possible, we try to authenticate the DNS messages that we receive, and the protocols that do that are called DNSSEC. So with DNSSEC, very similar to, we have the same problem in routing protocol in BGP, so exactly the same infrastructure is used. Records can be signed using the same public key cryptography system. And now in the root servers are the one that initialize the chain of trust. That means if you sign a record from the Epfl server, you will sign it with the Epfl key, and the Epfl key itself is authenticated with a certificate that is signed by one of the keys of the root servers. Some domains like Google do it systematically. In Switzerland, as far as I know, not all domains do it systematically, but in some countries, the local registers mandate that this is done systematically. So, of course, more and more of this is done, but this is a potential fragility here in the internet. An alternative, instead, DNS uses UDP. So when I send a query to a DNS server, it's over UDP, non-encrypted. An alternative is to use it over TCP and TLS, which is a bit more heavy, but some systems require doing it. And there is a development to do DNS over QUIC, which would fit very well also. TCP has the problem of head-of-the-line blocking and of the time it takes. As we know, DNS over TLS takes 2 round trip just to set up the TLS connection before getting any reply from the DNS server. With QUIC, we mitigate this, we make it less of a problem. So in the future, we will see whether those competing technology security improvements will be deployed, and we hope they will. There's also a poor man's DNS that you probably use every day without knowing it. It's called zero configuration, or by Apple calls it bonjour. In fact, it is when you connect to your printer that has a name here, you don't go to a DNS server, although you can put the name of your printer into your DNS server at home, but very few people do that. Instead, there is a special domain called local, which means anything that can be resolved locally without DNS servers by broadcast. So when your printer has a given name here, you know about if your computer wants to send to this printer here, the way it is done is by, very much like ARP, we would send a bonjour query that says who has this name, and your printer, if it's up, will reply, and then you can connect to your printer and send your job to be printed here. So it uses multicast technologies, unlike ARP that uses broadcast, but we know that we try to avoid broadcast. So this is the IPv4 broadcast address, and this is the IPv6 here. This is inherited from very old plug-and-play technology. The first Apple Talk machines in the 80s, they used exactly this. So when you would connect from one machine to the other, you would connect by name, And the way you would do that is by using this broadcast. So we see here always the competition between the two types of resolution. ARP does it by query broadcasting or multicasting queries. The DNS does it by using directories. Of course, we can use both. We've seen that we can fortify ARP by putting a directory in the switch instead of having a broadcast mechanism. In the similar vein, we can de-robustify the DNS, but make it more plug and play by replacing a DNS server by local queries. Of course, as you can imagine, this works only in a LAN. Right? If you try to send a broadcast query or a multicast query to find the name of my printer when you're not at my home, then it won't work. There are various protocols that do it. I'm citing a few here. Okay, so time for a little quiz. Assume all DNS servers of Epfl go down. How long does it take for the whole world to become unable to reach Epfl services? I close the poll in a few seconds. And of course, the answer is B, because in this hypothetical example here, the TTL is 2 minutes, which of course Epfl doesn't do, but if Epfl would do it, that means that if all servers will go down, then all the cached values, if nobody manipulates the caches, will expire after 2 minutes, which means it's quickly unreachable. In fact, Epfl does the other way around. It does it, I believe, 1 day or even 2 days, because Epfl is not supposed to be so dynamic, which has the opposite problem, that if we change a DNS record, the time for this to percolate through the entire internet is as long, in the worst case, as the TTL, because you have cached values that will still be considered valid by the local caches. So if you take 1 or 2 days, which is typically done by static sites that do not use multiple data centers that you connect to. If you don't have this load balancing problem, very often the values are order of a day. Question? Yes, that's called a cache. This remembering is the cache. That's what I said. If the cache has not been tampered with, the cached values have a TTL. They are valid for 2 minutes. So when your DNS query comes to the cache sees, oh, I have something, but it's no longer valid. So normally the DNS protocol in such a case says, I don't give you the value. I don't return the value. Of course, I can. I can tamper with my DNS server, either by writing a script that will modify all the TTL values. I could go to my logs and find what is the old value. So if you're a hacker, there are ways to still get the IP address, of course. But the intended behavior is not. And in reality, most DNS caches would not like to do that, because the normal case when the name has changed is because the name is somewhere else. Perhaps we've changed the DNS supplier. If you buy your own name, you will need to buy from somebody a service that puts your DNS name into their server. But you changed that. You did it with Switch, now you do it with Infomania. So the thing has changed, perhaps not because of this failure here, but because it's a true change here. So if a cache that would return the old value would simply return an IP address that perhaps doesn't work. But of course, if you are able to hack, you can hack and everything is possible in the software system. Yes, question?
For the example that you gave about TCP-IP having a cache for TCP days, what then would happen to you change the IP and I try to connect to the developers in my cache? This IP is not existing. So will I just flush my cache and request to the DNS again, or might it be
No, so assume Epfl has a long cache, let's say 1 day, and then Epfl decided to change something, then it will not work. Other systems will get a reply to the IP address that is not the one that Epfl uses today. So it will not work. Unreachable, or most of the time, and if you run a web server, you don't destroy the old one when you do a new one. You typically add a new something, and then there will be an interim period where the switchover will not be instantaneous, so people will have the old version. So it will take some time to get the new version. Voilà, that was for the DNS. Now let's look at a topic that is, in principle, not very important, but plays a role, application layer gateway. An application layer gateway is in principle against the philosophy of the internet, because we said the application is end-to-end, and the internet is made of routers, essentially. If you remember, at the very beginning of this course, the old computer networks used application layer gateways all the way. But the invention of packet switching was the great thing that made this possible. But still it exists. For example, web proxy. A web proxy is something that if I go to a web server, in fact, there's a machine on the path, typically at the border between an intranet and the global internet, that will capture my query, look at it, see whether it would like to reply to it, and if it likes it, will forward it to the remote server, and if not, might delete it, for example. So this is an example of what we call store and forward. Here there are two TCP connections from the client to the web proxy, and from the web proxy to the final server. So many web browsers allow you to configure a web proxy, for example. This is done by some companies here. It has a number of reasons that we'll see. But one important reason that we could imagine, based on what we've seen so far, is to avoid the problems of TCP. If you're accessing here the gateway over a network that is wireless and has a number of losses here, then the performance of your TCP connection is dictated by the link between you and the gateway. Then there is another TCP connection between the gateway and the server. This is typically on a wired network, so it will not have those problems. So you might have a large throughput between the two. And the throughput here might be bad because of the losses, but you will have a short RTT. So you will have a throughput between A and the gateway, a throughput between the gateway and B, and the available throughput for end-to-end is the minimum of the two as a first approximation. Of course, it is a dynamic thing, it varies over time, but if things are stationary, is the minimum of the two. So this is a gateway. Of course, the gateway adapts the different rates of the two TCP connections, which means it may require to have a large buffer. If, for example, the link over the internet is much faster than this one, then the download from the server will fill the buffer here until the socket buffer here, until the gateway logic is either unable to read it, so the socket buffer through the window size acknowledgement will stop the B from sending, or if the gateway logic is able to work, then it will be able to pass it. Yeah. This was used very much in the past to cache data, to avoid having to commonly use data. For example, if everyone at Epfl stores gets access to the same information, then you can store it locally in the cache, very much like DNS servers do. This is much less done today because everything is encrypted end-to-end. So instead, what is done today is HTTP tunnel, which is the modern form of this gateway. When you go to an HTTP proxy, you open a TCP connection to this proxy, and then you will typically open a TLS connection to the remote server. So the TLS connection the TCP proxy will not be between the TLS connection. So it will let the TLS connection be repeated without any change, because the goal of the HTTP proxy is that it doesn't know your secrets. If it does, then it's not very secure. So we see here that we open one TCP connection from client to proxy. The proxy opens one TCP connection to the server, and the server, in fact, replies to the proxy, which is a true man in the middle. As I mentioned, the end-to-end principle is excluding that. So the end-to-end principle says that we should not do it. That's one of the design decisions of when people do distributed systems. But as we have seen with performance, there's a good reason not to do it. For example, imagine we would apply the end-to-end principle for email. Today, when you send a mail, you have at the minimum 2 servers. Not at the minimum, you may have only 1, but very often you have more than 2. So you send mail to your mail server. Your mail server sends it to whoever you are sending the mail for, and then the final destination will get the mail if you use POP or IMAP, or a web browser will go to a server to get this application. If we would use the end-to-end principle, then we would run a mail program we would directly open a TCP connection and run the mail protocols from source to destination, which is what we did long ago. But of course, nobody is interested in doing that today for zillions of reasons, but essentially 2. One is mobility, availability. I mean, when I send you a mail, I don't expect that your computer is up and running or your smartphone at the time that I send you the mail. So the availability will be taken care of by the servers. And also security. I don't want anybody to be able to send a TCP connection into my machine. I prefer to connect to Outlook of Epfl or to Gmail, where I hope those systems are well maintained. So the end-to-end system is not always applicable. Here is another example where the end-to-end principle, the end-to-end principle is broken. When you go to a data center, this is typically what happened. We've seen that we can use the DNS to decide to which data center we go. But inside the data center, there's again the same problem. The data center is thousands or tens of thousands of servers. So when in fact you interact with a server, you interact with one of the many server machines that are in the data center. So what is typically done is that your query is first intercepted by a proxy, which is now server side. It's not a proxy on the customer side like I showed before, but a server side proxy, which will do the same thing, but on the server side. And then based on local load balancing algorithm, will send you to one or the other servers. So of course, the assumption is that here, the job of this machine here is very shallow. It doesn't need to do a lot of work. It will simply examine your TCP connection opening, perhaps your IP address, perhaps apply a number of other filtering rules. But at the end, there will still be a TCP connection between you or your client-side proxy and this machine, and another TCP connection or something else, which might be quick, for example, if you're going to Google, between the load balancer and the data center itself. How is user traffic split among load balancers? Well, if you have a load balancer, it becomes the bottleneck of your system. So you may want to have multiple ones for performance. And certainly for robustness, you should have at least 2. So the question is, how could we split the traffic among load balancers? We could use DNS, but DNS is more typically used to go to different sites. So inside a site, we use what is called equal cost multipath routing. So the DNS will give you one IP address, which is the IP address of this data center. In fact, this IP address is allocated to all the load balancers. And if you remember OSPF, how does OSPF work? An OSPF router can believe that it's connected, it has a path to a certain IP address, so it's directly connected to an IP address. We have seen that when we have areas, for example, a border area router says, I am connected to this prefix. And another area border router might also say, I am connected to this prefix. So multiple machines can inject into OSPF the same IP address. It's never a problem. OSPF will compute the shortest path. And if there are equal cost multipaths, we'll use multiple paths to go there. So we do exactly this. This is called the use of an anycast address. Anycast means an IP address, a standard IP address, that is allocated to multiple machines. So there are multiple machines that have the same IP address here. If you don't do it carefully, it will not work. But if you inject this well into the routing infrastructure of your data center, and if you do equal cost multipath routing, then the different queries will go, if you have, for example, 16 load balancers, they will go to randomly one of the 16 load balancers here. So this is how all those different things are practically combined in data centers. Application layer gateways are also very often used in what is called Untrust Zones. Epfl has that. Practically all companies have that. You typically, my internet connection is unstable, okay. We typically do not connect the intranets to the rest of the world without any precaution. And for example, many servers of Epfl on which we do Lab 3, for example, they are not on machines that are open to the entire world. They are in the Epfl zone here. And similar to what I presented here as a load balancer is an example of things that you may access as intermediate point before going to one of those servers, and also some of the web servers. So many web servers that are available to the outside, they are put on special machines that are in a special area, which is called an untrust zone. So it's an area that belongs to Epfl, but where the machines are exposed to the entire world. So if they are exposed to the entire world, that means a number of things. I mean, first, they should not, the probability that they are compromised is not negligible. It can happen that they are compromised. So if they are compromised, that should not be a catastrophe for Epfl. So we should not be able to get all the information about your academic records, for example, on those machines. They should be here. And the second thing is they should be scrutinized by the system managers of Epfl when there is, for example, a zero-day attack that is possible, like happened last week, last Friday. They will quickly disconnect them or patch them very quickly. So this is another use of the firewall. So many times when we connect to an Epfl server, in fact, we establish a TCP connection to one of these machines that are not the final destination. And this is very typical. So a quick recap on this. I'm assuming here in this quiz that I'm accessing the data center and a packet is lost in the transfer from the data center to Lisa. Which system will retransmit it? I close the poll in a few seconds. Closing. And there's a large minority that says D, but this is precisely the thing that I would like to illustrate here. No, the answer is A. So there is one TCP connection, or quick if you in the future would use QUIC with a load balancer. So a TCP connection means the endpoint of TCP is here. So the packet retransmission will happen here. If this is truly an HTTP, if it's an application layer gateway. And of course, this is independent whether we use QUIC or TCP, the same happens. So it has also the effect by breaking the TCP connections of having this retransmission done here. And also that, for example, in the data center, we can use versions of TCPs that are working well, but work well only in a data center, like DC TCP. We can use that version here and another version there. Application layer gateways are deployed, therefore, for security, performance, but there is another topic that sort of poisons the internet for the coming years. That's the interworking between IPv6 and IPv4. Remember that IPv6 and IPv4 are incompatible. You've seen that from lab 3. And you have a problem if you have only IPv6 access, you want to talk to a server that's only IPv4, because it's an obscure server somewhere in the world that nobody has taken care of porting it to IPv4. And believe it or not, but in the private environments, we will see why in next week when we study MPLS and VPNs, most applications are still being run and deployed today for IPv4 only. I hope your generation will break this, but because this is still happening, there's a lot of IPv4, there's not enough IPv4 addresses, so modern systems will have only IPv6 addresses here. So we will have to solve this. So the first problem that we're concerned with is if we are modern, if I have software system, of course I will have IPv4 and IPv6 because the cost of having that is 0 today. If you're up to date with your operating system, you of course have both IPv4 and IPv6 here. Now assume here I have a number of servers in the world, but some of them are both dual stack, some of them are only v6, some of them are only v4. Now assume I connect here. To which of the two will I connect? Well, many systems by default prefer v6. So if that's the case, this system would connect to the v6 version of this server here. Sometimes systems, when they move from IPv4 to IPv6, what they do, they create another copy of their website that works on IPv6, and they, for at least for some time, maintain both here. So the question that is here done is, how will this machine know that it should go to that version of the website, the one that runs on IPv6? How do you believe that things happen? In this example, the website is the website of Epfl in China, and it works only on IPv6. This is a hypothetical. I close the poll in a few seconds. Closing. So there's a good distribution on this. We could try a ping 6 and a ping 4. You could do that, but that's very unfriendly. First, it might be that the ping dies because some systems kill pings on the way. And it's also not friendly to the remote server. I mean, before connecting to a server, you first send a ping to that server. So it's creating useless work. And many servers will protect themselves from pings because the denial of service attacks, so that would not work. You could do this. And perhaps this is what you did in your lab 3 when you had to connect to both servers. But it's also not very friendly, right? Also, there are risks that both work, and then you will get both. And if they are overlapping, you will not use your resources and those of the server very efficiently. But we've seen another way in lab 3 to do it. The other way is to use a DNS. So when you connect to a server by name, you will, I think the modern technology, the one you should use for whatever you do starting from this course, is to always try to have all possible address formats, which are IPv4 and IPv6. So modern software will ask both questions to the DNS, what's the IPv4, what's the IPv6 address, and see what you get. If you get only an IPv4 address, then you're stuck, you should use IPv4. If you have only IPv6, you're stuck also, you should use IPv6. If you get both, then it's up to the algorithm that runs in your machine to decide which one to use. Many machines use by default IPv6 because it's more modern. Some other machines, like some versions of macOS, I'm not sure it's still true today, will try to keep a trace of how good one works and the other not. So this is another example where the DNS helps us. The DNS that was meant to solve the problem of only readability, all of a sudden we see here can be used to solve the problem of IPv4 versus IPv6. That's one of the key ingredients in the transition to IPv6, because a name is independent of the type of the IP version. So when we move our system to IPv6, for example, we simply add a new IPv6 record for the same name. That was that's in principle the transition that many companies will use. By the way, when we say DNS, we saw that DNS. Yes, question?
When you say that you could try to connect to your site using IPv4 and IPv6, like things in order to ping the content?
No, I would not ping. As I said, pinging is not a very friendly operation, and it's for you because it might not work. Very often, if you try to ping IBM, the servers of IBM, you will never get a reply, for example. So it's not very efficient, and it's also not friendly for the other side, right? It's like before sending you a mail, I first send you a WhatsApp to tell you I send a mail, okay, but you might as well say everything in the WhatsApp. So that's the same nature. And you will need to go to DNS anyhow. Well, it's up to you. I mean, you could program the DNS wrong. Because when you do get host by name, you can say, you have to say what's the protocol type. So you can get host by name using only IPv4. And then you will get only an IPv4 address. And then you could do this and forever use IPv4 in your machine. What I'm saying is you should always try IPv6 by going to the DNS. Now it's up to your machine. You can go to the DNS twice if you want. That's your problem. You can go to the DNS to see if you get an IPv6 answer. If you don't get an IPv6 answer, you go again and get an IPv4. That would be an application that gives precedence to IPv6, always wants to do IPv6. Now, because some operating systems manage that for you, what is best, IPv4 or IPv6, it's better to do both and see how it will work. Sometimes IPv6 is not better than IPv4. We hope IPv6 is better because it's more modern, and dogma is that more modern is better. And it's often true. But sometimes we have seen in the lab, for example, we use Teredo, which is like a hack that we will explain also in a few more minutes, that uses very indirect tunnels. So that is typically less efficient than IPv4. So if you're going to a site and you don't have IPv6 and you use Teredo, for example, everything will be slower. And if the other site has IPv4, it's better to go with IPv4. This is why some operating systems try to guess and see what is best and is working best. Hopefully all those questions will disappear in a few years when everything works with IPv6. But when I see what happens in the industrial world and in private companies, there is still a lot of IPv4 being developed. So perhaps we will be there for a long period of time. We use the DNS to play between IPv4 and IPv6. Fortunately, the DNS is completely independent of which layer you use, which version of IP you use to access it. So a DNS server that has only IPv6 records should be reachable by IPv4 and vice versa. So if you go to the V6, if you enable IPv6 only in your machine, you should be able to get IPv4 queries here. So in principle, or vice versa, if you have an old installation where the network supports only IPv4, then you put your DNS server only on IPv4, because if you have only local network that works there. So there should be full independence of that. Voila, that's the end of this first hour. In the second hour, we will see how this can be used to simplify some of the cumbersome interworking scenarios. And after that, we will move to the last chapter of the course. So we resume in 15 minutes. This leads us to the next topic that we will discuss today and next week, which is the interworking of IPv4 and IPv6. As you remember, with very few exceptions, we may have V6 hosts, dual stack V6 hosts are able to accept IPv4 packets in an IPv6 socket, but a pure IPv6 host cannot handle IPv4 packet and vice versa. Therefore, the two are truly incompatible. And this is very complicated, or it's not so complicated, but the solutions that are proposed are, there's a broad spectrum of them. To make some simplification in this story, I think it helps to it helps to make the distinction between the type of problems we have in the interworking. The true interworking problem is the one I mentioned when you have an IPv4 application that wants to speak to an IPv6 application. That can be because you're trying to get to a web server of the library that until recently worked only with IPv4, or it may be the other way around. You have an Android smartphone or an iOS smartphone that has only an IPv6 address because you're in a cellular network telephone that has only IPv6, and you want to connect somewhere to somebody who's using Skype or Zoom or something that has only IPv4. This is interworking. There is a family of other problems that are easier to solve, but are more for but are equally important, which I call a like-to-like access. It is when your machine is IPv6, the other machine is IPv6, but the path between the two is not entirely IPv6. So you want IPv6 to talk to IPv6, but part of your network is not IPv6. That's a problem that many providers have now. Providers have set up their infrastructure with IPv4. Now they need to set it up with IPv6. If we would find a smart way to allow this interworking without upgrading everything to IPv6, perhaps some companies are interested to do that. And the other is even more pregnant, 424 over IPv6. If you have part of the network that uses only IPv4, and you want to still use an access that you have only IPv6 because your provider gives you only IPv6. That's the future. If you, in any country now, if you get new addresses, there will be IPv6 only because many providers don't want to bother doing complicated stuff to give you IPv4 address because new IPv4 addresses are not available. So if you use IPv4 in a provider domain, you typically use private IPv4 addresses. Like we've seen, there's the 10 dot addresses, those are the addresses that are given by Epfl VPN. If you're a provider, they use another block that is similar. But there's an easy thing we can do. And the easy thing is to go to the next slide. I'm stuck here. Same symptom as Roman in his physics, yeah. But assume, for example, here you're running, you're in an IPv4 enterprise. Everything is IPv4. They keep their software up to date, but still it's only IPv4 because the routers, for example, are only IPv4. We've seen that we can use a HTTP tunnel, a web proxy, for performance and security reasons. Well, that also solves the problem because this web proxy will need to repeat the TCP connection. Fortunately, there's only one TCP. There's not a TCP-V6 or a TCP-V4. So if this web proxy has an IPv6 access, then it allows you to go to any IPv6 service here. And vice versa, on the company side, if on the server side, you may do also put a proxy on the server side if your server infrastructure is running IPv4 only. So this is used, for example, when you have voicemail or other services that are typically running only on IPv4, then you can access them in this way. until recently, Epfl was doing this trick. Exactly, all the Epfl web services, before they were migrated to the cloud, they were running on Epfl servers on IPv4 only. And then what Epfl did was to do a web proxy that would have, which was www6.epfl, but it responded also to the name www.epfl and had an IPv6 address. So if you would be going to the IPv6 machine, you would go to this one that would simply go to the Epfl server. This was before everything was migrated and fortified with the trust zone. You could go directly, at least, to the Epfl servers that were exposed to the world. Now, how does your machine, if your machine is IPv6, how does it know that it should go to this server or to that? I guess the answer we all know from what we discussed is via the DNS. So if you do this trick, you will write in the DNS a different machine for www.epfl.ch. So for the same name here, you will put the record that are IP addresses of two different machines. The IPv6 address can be an address that is, it is an address that's different, so it can be also the address of a different machine here. So if you query the DNS and ask for an IPv6 address, you will get the address of the gateway. If you query the DNS and ask for an IPv4 address, you will get the address of the native system here. Which means in particular that if you, in this special case, if you would use IPv4, you would probably get a better service. And the last question is, what happens if you have both? Which is hopefully the case for many, but not the case for us here over Wi-Fi at Epfl, for example. We don't have IPv6 address access over Wi-Fi, so we're in the case of the previous slide. If we are in the part of Epfl that is made for us to be compatible with IPv6, which one will we use here? I close the poll in a few seconds. Closing. Then the majority of you says it depends on the configuration. Well, that's true. We don't know. In fact, this is both work. So the application will, because it's running on both IPv4 and IPv6, if it's well programmed, which is not certain, it depends on the application, but your web browser is a modern one, it will get both addresses, the gateway and the native machine. And then it's the choice of the operating system. Will it prefer IPv4 or IPv6? Many modern systems will prefer IPv6, in which case, by being modern, you get to the gateway, which has less good performance because you have a store and forward system. At least in the case of Epfl, that was the case. That one was not dimensioned with extremely high throughput, so it had not so high throughput and longer delay. That was a case where having IPv6 was less good than having IPv4. This also motivated some system developers at Apple, for example, to try to optimize things. Voila, that's our coverage of the application layer gateway. Of course, there are many more fascinating topics in the application layer, but they are largely outside the scope of this course. Instead, what we will do now is to, in this, we're getting to the end of the course, so I've explained beautiful things, hopefully, about how TCP-IP is organized and so on. Now let's look at the things that are a bit weird and less beautiful, but they are present because they serve the purpose at some point in time. That's what I call deviations from the architecture. So those are the weird things here. This long list of deviations is proxy ARP fragmentation, tunnels, 626, 624 stuff, and MPLS. So let's start with proxy ARP. In principle, IP says one subnet is one LAN. That's the same. It's just in the context of IP, we say subnet. In the context of, I don't know what, perhaps hardware and cabling, we say LAN. But for us, it's the same. Now, assume you have a configuration like this one. You have subnets that are interconnected by routers. You have a machine here, 12.12.12.4, that is not in the correct place. The subnet that has this prefix is the subnet that is between R1 and R2. And you have somewhere else on one port of R3 a machine that has the same, that should belong to this. So it's a configuration mistake. But it could be intentional. We will see examples where it could. And assume you want to make this work. So if you would do that at the quiz or the labs at the beginning, we would say that's wrong, 0. But in TCP-IP, everything is software. In software, you can have weird things. This is why there are lots of bugs in software, because you're not forced to do things right. And sometimes you do things in a strange way for good reasons. Assume for a second you want to do this. Of course, it will not work if you simply do this and put this machine at the wrong place, then it will not work. So if you break the architecture at one point, you need to fix your break. So it probably means you need to break the architecture at another point, at one or several other points. Here, what is done is called Proxy Arp. So there is an easy thing you can do, which is to do what is called host routes, which means you can manipulate the routing of R1 here to say that this prefix here, so it's a destination that is full length of an IP address, 32 bits. You put a routing entry for this. And since we do longest prefix match, any IP address that is in this domain here will be routed by R1 on this interface here. And it would say it's directly on link. And if you have a packet that goes, that is received by R1 and should go there, then it will follow this more specific address that says send to next hop, which is R2. And you can do the same in R2. In R2, you can say the normal here is on the left, interface ETH0, and this a more specific thing, and same in R3. So that takes care of the router and configuration tables, and it relies on the fact that we do longest prefix match. So we can do more specific things. So far, so good. However, it will not work for the hosts like A that are in this domain here. Here we probably have a switch network between the two. Now, if A sends a packet to this address, A doesn't know of the routing tables because A is not a router. Of course, the fix would be to put routing tables in all the hosts that are in the domain. That can work. But in principle, a host is a PC or a smartphone, so we don't want to play with this routing table. So what will A do is the usual IP architecture stuff. It says, this destination is on the same subnet as me, therefore I will do ARP in order to get the MAC address of this destination. Of course, I will broadcast it, or if it's IPv6, I will send a multicast packet. And of course, the destination is not there. Nobody will reply, and this will not work. So, but as you can easily imagine, there's an easy fix. We've seen that switches could reply to the ARP instead of the final destination. So we could have somebody reply to the ARP instead of the machine. This is called exactly Proxy Arp here. We could have, for example, R2, which is on the path to this machine here, reply to the ARP here. So this is exactly what would be done here. We can configure R2 to do what is called Proxy Arp for this specific address. So R2 will reply with its own MAC address. So R2 will pretend to be the final destination. That's why it's called a proxy. Proxy is whenever you do something locally in a machine instead of the ultimate destination. So R2 will do a proxy for all the ARP requests. So A will say, who has this IP address? R2 say, me, it's me. Send it to me. Here is my MAC address. It looks like a man-in-the-middle attack. In fact, this is exactly what you do when you do a man-in-the-middle attack. But here you can do it for a good purpose, which is to get the packet. Now, R2 gets the packet. Now, R2 analyzes the IP destination address. It's from its routing table. It says, I should send it to R3, and so it will work. So this is a way we can solve the problem. And strangely, it is done a lot. In fact, many places do it. An example when we do that and when we access via a VPN server, for example, this is the version before last year. where we had a VPN server. So you access it via a VPN tunnel. The 6500 CS is the VPS server here. When you connect to the VPN server, you receive an EPFL address, which last year was a true EPFL address. Now would be a 10.something address, probably. But that's the goal of VPN. VPN server gives you the impression you are on the EPFL address, which means in particular, you have a valid EPFL address. You're treated as if you would be on site. And of course, this gives you some security guarantees, because in order to do that, you will need to show credentials to the security system that goes around here. You will need to log in with your EPFL password and your username. So if your username or CamiPro account is compromised, it's easy to revoke the authorization to this. Yeah. So that's the goal of VPNs, is to decrease the perimeter of attacks by reducing the access to machines here. Now, from a protocol viewpoint, when you connect to the VPN, you get an EPFL address, which is, in fact, the EPFL address that's given, which is as if you would belong to the subnet here, 84, which is the subnet on which the VPN server is connected. In fact, there are multiple VPN servers for reliability and performance, but I show only one here. Now, this is the state of things. The subnet is both here and there, because in fact, I am connecting via the EPFL through the VPN server. The VPN server is a router, among other things. It performs a router function. So we are in the same case as before, where I have here a subnet, somebody that is not on the subnet, it's far away at the other edge of the router, but receives an address that is as if it would be on the subnet here. How do we solve this? Well, same thing here. It is the VPN server that will do proxy ARP for you here. So for example, when a packet has to reach you, so you do something on the, you do your lab 3, for example, the reply goes here. So this machine, ED0X, has a packet to send to you. So it has destination address 83.133. This one will do ARP, because it doesn't know of this trick, only the VPN server does it. What will happen? Who will reply to your ARP, to the ARP request of this poor machine in the middle? I close the poll in a few seconds. Closing. Closed. So of course the correct answer is A. That's the goal of Proxy Arp. Proxy Arp means I reply with my own MAC address because I want to attract those packets to me, and I will take care of them, which is what the VPN server will do. All the other answers, well, we can examine them, but they don't make sense because, for example, if you reply with the MAC address of Green Mac, well, the MAC address of Green Mac is of no use, right? The MAC address of Green Mac is usable only at home between me and my ADSL modem. But the MAC address of a machine that's not on the same LAN as you is not even visible to you. So there's no use of having this MAC address. It's useless. Green Mac could reply with its MAC address, but that would mean I send all the, I operate this as a bridge here, which would mean all the broadcasts would go via the long distance links, which is not something you would like to do. So that could work in some settings if we configure it as a bridge, but that's not desirable because of all the broadcasts that you would send everywhere. And again, here, if Green Mac replies with a MAC address, that would work, but that's also highly inefficient. So the Proxy Arp method consists in having the router or that is directly on the LAN on the subnet of interest reply with this here. So that's an example. It was used, for example, in the past at Epfl also to solve a stupid configuration issue. that Epfl had the address 128.178, also 179, but 179 is used only for the wireless domain. So in the wired domain, up to not so long ago, all routers of Epfl would do proxy ARP for all addresses of Epfl, 128.178. So if you send a packet from one machine at Epfl to another one, you would believe they're on the same subnet as you. Which means that if you, and the goal was precisely to allow this to be possible, because at those times people did not know so much of TCP-IP. So if you configure your subnet mask as being 16 bits instead of 24, it would work the same way. So for a long time, we had this configuration. That's an example of the kind of things that are done that are possible with Proxy Arp, which again is a hack, but is a hack that was used and is still used a lot. You are likely to see it happening somewhere. The next topic is fragmentation. So fragmentation is more a nuisance than a hack here. And it has to do with the table on the left. That is, so far we always did as if the packet size were 1500. We've talked a bit, alluded to the problem with TCP. We said when we open a TCP connection, we also negotiate what is the packet size, the MSS. MSS is a packet size as seen from TCP. That means that the IP minus the IP header. Sorry, the MTU is minus the IP header as well. And 1500 is a very frequent number, but it's not the only number. In fact, if you look at my machine here, when I look what is the MTU, I see that I have some interfaces that have a different value, smaller here and here, smaller there. So here it's because I'm on the Epfl VPN, and here it's because I'm on perhaps VirtualBox here. Even if the packet size is 1500, there are cases where you want it to be different. For example, you have high-performance systems that may have larger packet sizes. Fiber channel is an example. It's like a super-duper Ethernet, if you want, that allows bigger packet sizes. That's used at CERN when they dump terabytes of information from one server to the other. And because if there are fewer packets, then there's less processing to be done by all paths on the way. And if your system supports it, then it's better. There is header to be processed. So if you can do a transfer in 10 packets or in 100 packets, then the CPU required to process the 100 packet is probably 10 times less. So some systems use larger packet size. In the extreme case, when we use the loopback interface, in the loopback interface, we can have even a packet size of as large as whatever the operating system supports, which can be gigabytes. Right? If you use TCP-IP as an inter-process communication system with sockets to communicate from A to B, A and B being two processes inside your machine, you can do that with UDP sockets, for example. You can also use with TCP, but the probability of losses is extremely small inside your own machine. And then there's no reason to have a small packet size. Sometimes you have a smaller packet size, which is here we talked of the Epfl VPN tunnel. When you use the Epfl VPN tunnel, the packet size is much smaller. Why is it smaller than the regular packet size? Yes? So that you are sure it works on all the paths. That could be a reason, but there's probably another one more dominant. Well, when you use the VPN, everything is encrypted and authenticated. So when you send an IP packet, you sign the packet and you encrypt it. So all the signature, at least, will cost something, and encryption also might typically enlarge the packet. So this encryption, you put it into a tunnel that itself has its own headers, and this will cost something. When we use Teredo, we put all the IPv6 packet inside IPv4 packets, so we lose also the IPv4 header. So when you use a tunnel, you lose something here. Sometimes you have also systems that have the opposite, want to have very small packets. This is ZigBee is a kind of low power Bluetooth or lower power than Bluetooth that wants to have very short packets because this is very low power and very small bit rate. The packet size is not an issue when we're talking of links at gigabits, 100 gigabits, terabits per second, and packet sizes can be large. They are still small at those speeds. But when we're doing things at kilobits per second, packet sizes wants to be small. So you have some devices that have very small packet sizes. So all those packet sizes exist. Now, in the modern internet, for IPv6, we would not allow 80-byte packets. We want minimum packet sizes. But for IPv4, you can have a packet sizes that are a bit smaller. So ZigBee would not work with IPv4 here. It uses a native MAC layer protocol. But there is an issue. If you go from A to B, and A has a certain packet size, which is shown here, B as well, but in between, for some reason, there is a network that has a smaller packet size. Here I took a radically smaller packet size, 620, but you could imagine concretely, for example, that due to tunnels or security, you would have a smaller value. So a good example would be if we have a VPN tunnel between the two here. Of course, the correct thing would be to signal this end-to-end, and this is what we do in principle when we run TCP connections. With TCP connections, we try to have a mechanism to know what is the end-to-end MTU, but if we don't, then we have to do what is called fragmentation here. In principle, we try to avoid. So new applications should avoid them, but it's like many things that we discuss in the course. New is not everything. We will still need to live. You will probably need to live for the whole of your life with things that don't do it the right way. So with IPv4, we allow fragmentation. And the way it's done is simply, whenever a router receives a packet that is too large to be forwarded, so I have a valid path to the destination, but the path it does not allow me to have packets that are of that size. What the router may do, the router may refuse, it may send back an ICMP message saying, sorry, packet too large, I refuse, or it may accept to do it. If it accepts to do it, it will break the original IP packets into as many IP packets as required to fit, to contain all the data being of the correct size, not too long. In this example, we have here the original packet is broken into 3 packets, 3 IPv4 packets. The important thing to see here is there is no encapsulation, fragmentation, and reassembly layer like some systems do that would put the packet inside smaller packets and put it at the end, you will recover all the pieces. No, we don't do that. Here, instead, we say we simply break the packets, we fork in some sense, the packet into 3 packets, and each of the 3 packets are independent IPv4 packets. This is done by using a field that is one of the obscure fields we never looked at in detail in the IP header. In the IP header, there's a length field, and there is all those things here with the identification, the more, and the offset. What are those? The identification is a packet number. So when an IP source creates a packet, ping, it computes a number and puts a number in this packet. The next packet will typically be this number plus 1, or you can also randomize it, but you have to make sure it doesn't wrap around. This identification number is used for fragmentation to be able to identify that those 3 independent packets belong to the same original datagram. So here we see the number is the same. So at 1 is the original packet. The 2, 3, the 2A, 2B, 2C, they have the same identification. There is a bit that says whether it's the last one. So packet 2C will have this bit set. It's called the more bit. Set to 1 means there is more to come. And then the offset says where in the original set of data that were a payload of a packet, where this is. For example, for the first packet, the offset is 0. For the second packet, the offset is 600 because the maximum size is 620. The IPv4 header here, there's no option, is 20. So we can put 600 here, which means the second block is at an offset of 600. This is what is put in the second packet. And the third one is at an offset of 1200. In fact, what we write in the packet is not the offset, but the offset divided by 8, which saves 3 bits in the IP header, because the offset has to be a multiple of 8. That's one of the constraints of the fragmentation. So we do fragmentations in a 64-bit world. The other important point to realize is that once something has been fragmented, they are 3 independent IP packets. They live their own life. In particular, if there is multiple paths, if it's equal cost multipath, we know in principle we should send them over the same path. But here, if they're fragmented, we don't know what can happen. And if we don't do things that try to avoid different paths for the same flow, it is possible that the 3 IP packets, you do not violate the IP architecture by saying that the 3 IP packets follow different paths. So they may reach the destination in any order. Also, it may be that some of the fragments are lost, some others are not. It is always the destination that reassembles the packet. We could imagine that it's R2 that does it. That would be a way to do it. We could say, well, we establish a tunnel from R1 to R2, we break that into pieces and we reassemble it. That's not the decision of the internet for good reasons, because we know the internet, when they invented or they reused packet switching, the idea is that the routers should be as simple as possible. So routers don't want to reassemble packets. Well, as we will see, there's some work involved in reassembling packets. So R2 will not reassemble. R2 will simply pass 3 packets here. And if the 3 packets reach the destination, then the destination will use all those fields to reassemble the packet. For example, if it receives the second fragment first, it knows it is not the last fragment. It knows it is at an offset of 600. So in the socket buffer, I will put it somewhere with an offset of 600. Then hopefully it will receive the first fragment also, and this one as well. When it receives the last one, it knows it is the last one. So it knows I have a packet that has exactly that many bytes, because the length of the packet is the length of the fragment here. Right? This is not the length of the original datagram. We have lost all information about the original datagram. We will recreate this information by using the offset and the more bits. That's the only information that will help us recreate. By using the offset, we put the fragments at the correct place. If we find a fragment that has the more bit, we know it's the last one. And if there is no gap in between, we know we're finished. If we don't have a fragment that has the more bit, it means one fragment was lost, which will once in a while happen, which means that when you're reassembling, you must handle this. How do you handle this? Probably with a timeout. When you start reassembling packets, you put them in the socket buffer, and you start a timeout. If you time out before receiving all the fragments, then you have a problem. What should you do? If you're designing an operating system, you receive 2 out of 3 fragments of this IP packet. Well, the decision, because its fragmentation is at the IP layer, is to consider that the IP packet is invalid. So you will discard it. That's how fragmentation works. It's highly inefficient if you think of this compared to TCP. If you lose 200 bytes, you will not consider that all the other bytes that have been received are discarded. But if you do fragmentation at the IP layer, the consequences of those putting it the way it is that a missing fragment causes the entire datagram to be declared as lost. So assume we add TCP to this. So we have one TCP segment, which is contained in one IPv4 datagram. So in the context of fragmentation, a datagram means an IPv4 packet which has not been broken into pieces. Each of the pieces are also IPv4 packets that are called the fragments here. Assume TCP did something wrong somewhere such that this packet will need to be fragmented and one of the fragments is lost. What will TCP retransmit? close the poll in a few seconds. And the majority says B, which is the correct answer. Unfortunately, because as we have seen, the bytes that were in all fragments will be discarded by the IP layer trying to reassemble. I'll come back to the previous quiz in a second. But of course, this is highly inefficient. So if we use TCP, it is stupid to have fragmentation because losing part of a packet is the same as losing the entire packet. In fact, that was one of the ingredients of the major collapses that happened in the 80s of the internet. The internet collapsed because there was no congestion control, so it was doomed to collapse. But there were some events where it was even amplified by fragmentation. Because if the packet loss rate is 1%, for example, and if every packet is fragmented in 10 fragments, then losing one fragment causes the loss of an entire datagram. So it amplifies the packet loss rate. So fragmentation plus TCP don't live well together. Therefore, all applications should avoid fragmentation. Certainly if you use TCP, if you have an application that uses UDP and sends only one short message once in a while, nobody cares, and that's fine. But if you have also a streaming UDP application, you should avoid fragmentation. So if you code an application today, you should estimate the path MTU. Path MTU is the minimum value of MTU that works along the path between source and destination. Of course, paths are dynamic. This value may change. So there are safeguards. And one suboptimal method is to use a minimum value that should work always today. With IPv6, the protocol says that's the minimum value that should always work. An IPv6 network and an IPv6 host should always support this value, regardless of what you do. So that's a value that has been chosen. I don't know why it's not a round value, but that's a value that should be chosen. So if you do, for example, encryption and things like this, you have to make sure at the end of the day, any tunnel that uses all your encryption should still leave enough room for that amount of bytes here. For IPv4, the standard says it's 68, which is very small, which means in practice it's catastrophically small. But most implementations today, those networks that run 68, they are very weird things. And the weird things must be handled separately. So the MTU that is minimum today is considered to be this one. So all IPv4 implementations by default should be able to use this value. So if you code an application, you don't want to do path MTU discovery, then you should not use values that are larger than those, because those are the only ones that you're certain will work here and will avoid fragmentation. If you want to play, be more, have higher performance, in particular, if you run an IPv4 application, that's a fairly small packet size. So if you force all your MSS to be that size, that means that you will probably close to triple the number of packets that are required. If you want to be a bit more efficient, that is a kind of problems you have when you're running a server, and the CPU performance of your server plays a role. If you're 10% more inefficient than someone else, that's still at the end results into cost. You will need more servers and more money to run your data center. So if you want to go beyond, you should do discovery of the of the path MTU. So this is what server softwares typically do. There are multiple methods. One that works by using ping messages, but that doesn't work well because we're never sure that the error messages are correctly sent by routers. So one way to do it, which is this method with a very long acronym, packetization layer path MTU discovery, consists in always monitoring the size that works. And you, for example, if you run TCP, if you have TCP acknowledgement, or if you have a streaming application that uses UDP, you probably have a logic that can know what worked and what did not work. So you will, for a pair, for every remote correspondent that you have, you will try to estimate this. So in the table of remote correspondence, that we see when we do netstat, for example, you will see your estimate. So for every packet that you sent that had a given size and was acknowledgement, you know this size has been working. You will start perhaps for the lower value, and once in a while, you will try a larger value. Now, there are not zillions of possible values. Not every byte value works. There is only a small number of values that are currently working in the technology. We've seen some examples in the slides before. So we'll jump to the next slide, to the next values that work. And if you still get acknowledgement, you will keep that. If it doesn't work, then you will go down again, and by going back perhaps to the lowest value and try to go up again. So something similar to what we do in TCP with the congestion window, but here with a different setting to try to have as large a packet size as possible while avoiding a fragmentation here. Of course, if destination is on link, that means the same LAN as you, then your path MTU should be equal to the MTU that's configured in your interface. Now back to this quiz that I promised we should do. Now assume we do UDP. What can we say about the port number? Is it always present in all packets or not? Here. It should be open. I close the poll. Close the poll soon. The majority says A, which sort of makes sense, but the correct answer is B. Because of fragmentation. Remember, we talked a lot of TCP, and we should avoid fragmentation. But UDP is message-oriented, and UDP allows a message to be up to 64 kbytes, which is larger than the IP packet size. It's done as a commodity to the programmer. When I receive data from a UDP socket, I know this is a block of data that was the entire block sent by the source. I don't need to have \n or whatever, analyze the strings to know whether it's the end of the block or not. I just know this is exactly everything that was received. As a consequence of that, it is possible that UDP fragments at the source. So if I create a UDP message, so if I pass it into the socket, this message is 1600 bytes, doesn't fit in one packet. Then UDP will create one IP packet that will be fragmented in the IP host. Therefore, there will be two IP packets that are created. This will be reassembled at the destination, and the UDP socket will see only one thing. Right? This is how UDP works. The consequence of that is that the second fragment, so this is when a UDP message is fragmented at the source, which may happen not so infrequently. Of course, it may also happen inside the network. If a router fragments a UDP message, then the second fragment does not contain the port number, because the port number is at the beginning of the packet. Right? From the IP viewpoint, the UDP header is at the beginning. At byte 200, there's only the UDP data. So you will have fragmented packets do not containing the first fragment, which is a big problem for NATs. So if you have a smart NAT, it will handle this. So when it sees a UDP or TCP, that should not happen a lot, but when it sees a first fragment, it remembers. So it will look at the IP address, the identification, and the port number. When a subsequent fragment arrives, from the identification and the IP address, it can derive the port number, which is not in the fragment, but is remembered by the NAT. Some NATs don't do that. I think one of the NATs we used in the virtual versions of VirtualBox that we had doesn't do that. So therefore, some of the things do not work. Voila, so that's all for today. So we've seen the dark side of the IP protocol. Fragmentation is one of them. Fragmentation in IP, I should have mentioned in Ipv6. So there's a difference, Ipv4, Ipv6. In Ipv6, we forbid fragmentation by routers in principle. So the example I gave is typical of Ipv4, but in Ipv6, it may be that the source fragments a packet because of the convenience of UDP that I mentioned, but routers should not do it. Voila, more next week.